Good morning, everybody. Welcome back to Abstract Algebra. Plan for today is order. We're going to talk about what the order of a group is, what the order of an element within a group is, and what relationship do these things have to each other. Where does office hours go? Like I promised on Friday, I'm not going to have my office hour this afternoon because I have to go sit in on someone else's class. Tomorrow, though, I will have office hour from 10 to 11. Yes, I know that's normally 10 to 11:30, but I have a department meeting at 11 tomorrow, so that gets cut a half hour short. So tomorrow, office hours from 10 to 11, 1:30 to 2:30. And on Wednesday, the usual office hours, the hour before class and from 2 to 3. What is the best cure for a bad case of the right angles? The best cure for a bad case of the right angles is the Pythagorean theorem. So, does anybody have any questions or comments before we get started for today? So it may look like a new topic for today, but we're still going to be working within the packet on cyclic groups that I passed out last week. Because while today we're sort of going to be talking about cyclic groups, but not really. What we're going to be doing today is going to be part of our ultimate big proof of the fundamental theorem of cyclic groups, which will be coming later this week. We just need to take a little bit of a detour here for a class to talk about something that's related to cyclic groups. That being the notion of the order of a group. So if you're following along in the packet, I'm on page 1, 2, 3, 4, 5, where it talks about where order is bolded at the top. So in general, the order of a group is just the number of elements in a group. Which, if G is a finite group, then it's just straight up the number of elements in G. If G is an infinite group, we just say that the order of G is infinity. Dr. Gerstle, infinity is not a number. Yeah, I know. But we need to have a term. We need to have some way of defining order of a group that is acceptable for both finite and infinite groups. And so for finite groups, it's just the number of elements in the group, but if it's an infinite group, then it's infinity. But Dr. Gerstle, I took real analysis, and Dr. Hutchinson taught me about different sizes of infinity, with like cardinality and stuff. Yeah, well, this isn't real analysis. We're going to just say all infinite groups have order infinity, and we're not, and in this class at least, we're not going to distinguish between different sizes of infinity. So let's do a few examples. Order, by the way, we're going to use absolute, like these vertical bars. No, that does not mean absolute value in this context. Here are the vertical bars. If we put it around a group, G, this refers to the order of G. Doesn't really make sense to talk about what's the absolute value of the dihedral group. Speaking of which, what would the order of D3 be? How many symmetries are there on an equilateral triangle?
6.
There are 6. E, R, R squared, S, RS, and R squared S. What did we say was the order, was the number of elements in the dihedral group in general on a regular n-gon? For D3, it was 6. For D4, it was 8. For Dn,
2n.
It's going to be 2n in general. About the integers. Are there 1, 2, 3, 4? How many?
Infinite.
there are an infinite number of integers, so we'll say that the order of the group of integers is going to be infinity. What?
My integer symbol just looks really good. So I was just proud of myself.
Congratulations. Takes a while to get integer symbols that look any good, and mine's still not the best. How about the order of the group of units in modulo 10? I'll give you a hint. So remember last time we talked about the group of units being the set of all integers less than or equal to, in this case, 10, that are relatively prime to 10. So last Friday we said that for 10 that was 1, 3, 7, and 9, and that these will always form a group under multiplication mod n. So what would the order of this group be?
4.
1, 2, 3, 4. I declare a thumb war. This is a tougher one. What? And this one doesn't have a nice formula for it, but how can we describe in general what the order of the group of units mod n is going to be? I say none of you have taken number theory, so you haven't seen the name for this. It's Euler's phi function. Elaine, what?
That's just confusing. That's just a symbol.
So this is the Greek letter phi, and in this case, phi of n is a specific name, specific function in number theory called Euler's phi function or Euler's totient function, which is defined to be the number of integers less than or equal to less than x less than n that are relatively prime to n, that have no common factors, in other words, with n. So this is something that shows up a lot if you were to, say, take a class in number theory, just a number of integers that are relatively prime to n and that are smaller than it. For 10, this was 4 because there's only going to be 4 integers strictly between 0 and n, 0 and 10 that are relatively prime, 1, 3, 7, and 9. 2, 4, 6, 8 all share a common factor of 2 with 10, and 5 shares a common factor of 5 with 10. And so in general, the order of the group of units mod n is going to be given by this totient function.
What does that function look like?
It looks like that.
But there's not like a formula for it?
If only life were so nice.
I was gonna say, because then couldn't we figure out how many prime numbers there are?
I was going to say, this is a complicated, this is not something that there's a nice, easy closed formula for. There are ways that you could certainly approximate it using, say, logarithms and such, but this is not something that has a nice formula that I can write down on the board. It's not n squared minus 2 or something.
Got it.
So if you ever want to evaluate this, it's going to take a while for any specific value of n. You actually need to go through and check.
Cool. Thanks.
Okay, good question though. So order of a group is just the number of elements in a group. Here's another notion of order. You can also define the order of an element in a group, in which we say, given some group G and an element little g and big G, we can also define the order of G, which we denote similarly. We have little g and we put these vertical bars on either side of it. And that's going to be the smallest positive integer n that satisfies g to the n is equal to the identity element in the group. So it's the smallest number of times you need to take g star itself in order to ultimately end up with the identity element. And if you take g to the n and you never get the identity element, no matter how many times you take g star itself, then you just say that the order of g is infinite. So it's infinite if g to the n is not equal to the identity for all positive integers. So, can be finite, may also be infinite depending on your group and the element within the group. Yeah, Nick?
So would the order of the identity be 1?
Indeed.
Okay.
So in any g, the order of the identity element is just going to be 1 because that is the smallest positive integer for which if you take e star e that many times, namely you just take a single copy of e, that will give you the identity element. Yeah, good question. Let's take a look in D3 for a couple examples. My notes are wrong on this matter. Let's do D4. I just realized that all the examples that I left myself notes to do are in D4, not in D3. So what would the order of R be in the dihedral group D4? Remember, R is a 90-degree rotation of a square in this context. In other words, how many times do we need to compose 90-degree rotations in order to get back to the identity? One? 3?
3 more rotations?
3 more rotations, so how many in total?
So 4. Wait, I don't get what you're asking.
Yeah, I'm trying to get to 4 because R to the 4th is the identity in the group D4, and R to the K is not the identity for all K strictly less than 4. R is not the identity, R squared is not the identity, R cubed is not the identity, but R to the 4th is the identity, so the order of R in this group is going to be 4. So riddle me this. If we were to take R to the 8th in this group, we would get the identity. But R does not have order 8. Why is that? If we were to take 8 copies of a 90-degree rotation and compose them all together, I mean, it doesn't twist enough to do that. I claim we would get back to just the identity transformation where we end up doing nothing as a net effect. But the order of R is not equal to 8. What's that?
It says the smallest n.
Bingo. So here, the fact that the order of d needs to be the smallest positive integer n, that'll make this happen. In general, there can be infinitely many values of n that'll do this. In this case, r to the power of any multiple of 4 will give you the identity element. But 4 is going to be the smallest number of times to compose r with itself that'll get you there. So smallest is important so that the order ends up just being a single integer rather than infinitely many potentially. How about s? Remember, s was just a reflection down kind of the diagonal of the square. How many of those do we need to get to the identity?
2.
This one's just going to be 2. But on the integers under addition. Can anybody give me an element within the integers that has finite order?
Oh. Okay, never mind. Are we at 0?
Yeah.
Okay.
Identity element always has order 1, doesn't matter what group you're working in. So 0 is going to be 1. What about the order of 1?
Infinity?
Infinity? You're telling me the absolute value of 1 is infinity?
Maybe.
Well, no, the absolute value is not infinity. But the order of 1 as an element in the group of integers is going to be infinity, since 1 plus 1 plus 1 plus 1, etc. will never give us the identity of 0. And in fact, in this group, in the group of integers, 0 is the only element of finite order. If you take any other integer, the order of that integer in this group is going to be infinity. Because if you take whether it's 1 or 2 or 5 million or -1 or -3, adding that element to itself over and over and over again is never going to give you back 0. But 0, of course, you only need a single copy of 0 to get 0. So just like in every other group, the identity element in this group does have order 1. Any questions or comments about what I mean by the order of a group or the order of an element within the group? I got a question. Dr. Gerstel, why are you using the word order to refer to two different things? This is a little bit annoying. I've just said, used a single word to talk about two things. The order of a group is the number of elements in the group. The order of an element is the smallest integer that we need to take that, that we were composed with that many times, we get the identity. Why on earth would we use the word order to refer to two separate things? A, it depends on the context. If you're talking about a group versus an element in the group. Group, it always means number of elements in the group. A single element just refers to the smallest number of n. So that's A. And B, there is a connection between the two. Here is the connection. We could say that in general, for any group G and any element A in G, I claim that the order of A is going to be equal to this thing. What is this thing on the right? Order of A is just the, you know what this is? This is going to be the smallest n such that A to the n is equal to the identity. What is this expression on the right? But say the order of A in these brackets thing.
Is that the order of the group generated by A?
Exactly. It's the order of the group generated by A. In other words, it's the number of unique elements in the group A, generated by A, which if you remember, is going to be A squared, A cubed, etc., as well as A inverse, A to the -2, etc., and the identity element. So the group generated by A, the cyclic group, the sort of groups we were talking about last week, which are the groups that are made up of powers of A inverse, and the identity, I claim that the order of this group, meaning the number of unique elements in this set, is always going to be the same as this, the order of A, the smallest positive integer necessary to make A to the n equal to the identity element. This is not an obvious fact, by the way. This is going to be a theorem we're going to try and prove today. But before we start proving anything, I would like to look at an example of this. Let's say we were to look in the dihedral group D3 this time. So in the dihedral group D4, we said that our 90-degree rotation had degree 4 because it took 4 copies of R, 4 90-degree rotations to get back to the identity. What would the order of R be in D3, where R is a 120-degree rotation on a triangle? How many 120-degree rotations do we need to get to the identity? We are going to need 3. But on the other hand, if we were to look at the order of the group generated by R, let's see what's going to be in this group. Well, can anybody give me an element in the group generated by R? Gotta have the identity. I also have any ideas for which element could be in the group generated by R. R. Any others?
Inverse of R.
R inverse. What is R inverse?
R squared.
R squared. Which happens to be R inverse because the way you cancel out 120 degrees of rotation is by doing 240 degrees of rotation. In other words, 2 copies of R. And it's going to turn out that's it. Because R cubed is going to give you the identity element again, so then it'll start wrapping around. R inverse is just R squared, which if you start taking that over and over, you're just going to get ER or R squared every time. So this is a group. How many elements are in this group? Okay.
3.
You guys. So it turns out that the order of R is 3, since 3 is the smallest k. With R to the k equal to the identity element. Smallest positive integer that we can take R to the power of to get the identity. And it's also the number of elements in the group generated by R as a subgroup of D3, because that group had 3 elements, E, R, and R squared. So in this particular case, the order of R turned out to be the same as the order of the group generated by R. And my claim is this is going to be the same no matter what your group is and no matter which element you take in your group. Potentially, these could both also be infinite. So like in the integers, for instance, we already said before that the order of 1 is equal to infinity, because you take 1 plus 1 plus 1 plus 1 over and over again, you're never going to get back the identity. But if we were to take the order of the group generated by 1, which, since 1 is a generator of all of the integers, this is the same as taking the order of the group of integers, that's also going to be infinite. So depending on the group and the element in your group, this could just be saying infinity is equal to infinity. Or if you have an element of finite order that generates a finite subgroup, it could be saying something like 3 equals 3, depending on the context of what is your group and which elements in your group are you taking. But we're going to show today that the order of a cyclic group is equal to the order of any of its generators. Would be another way to rephrase this here. Any questions or comments before we start proving things? Okay, so we haven't really proven anything in a little while. Kind of been since our subgroup packet that we actually proved some stuff. Here we're going to get into some big heavy theorems for the rest of the packet. And so this is going to be the longest theorem, both to state and to prove, that we've done so far. I'm not going to prove this theorem. What's that?
We just like that you left 2 pages for it.
2 pages for this proof?
Yeah, it's that long.
Yeah, it is long. I squeezed onto 1 page, and here's my notes on it. So I'm not actually going to prove this theorem specifically. I'm going to prove a more general theorem, and then this theorem will then be an immediate consequence of the bigger theorem that I'm going to prove. So here's the big theorem. We're going to let G be a group, and we're going to let A be an element of G. And I'm going to claim 2 things. First thing I'm going to claim is that if A has infinite order, meaning A star A star A star A will never get you to the identity, then I claim that A to the I is equal to A to the J if and only if I is equal to J. And second, I claim that if the order of A is equal to some finite value n, then I claim that the order of A is going to be, or the group generated by A is going to be this set specifically. It's going to be the set containing E, A squared, up to A to the n minus 1. And I claim that A to the I is equal to A to the J if and only if, that's IFF, n divides I minus j. In other words, if I minus j is a multiple of n. Holy Toledo! That's a lot to write down. So before we start proving, I want to just kind of go through each step and see what this is saying. So if the order of A is equal to infinity, then A to the I is equal to A to the j if and only if I equals j. You may remind me, we've seen one of these sorts of statements before. What do we mean when we say if and only if? So we're really saying 2 different things when we say something is true if and only if something else is true. Okay?
The statement is reversible.
The statement is?
Reversible.
The statement is reversible, meaning if this is true, then this has to be true. And if the second part is true, the first part also has to be true. This is my 105 class. I'd say they're logically equivalent statements. Both have to imply the other. So I'm going to start by proving number 1. So as always, we're going to start with let G be a group. And A can be an element of G. So our first case is going to be if the order of A is infinite. And we're going to then prove A to the I equals A to the J if and only if I equals J. So if the order of A is infinite, what does that tell us then by definition has to be true about A? What did it mean to say that A has infinite order in a group? What?
A to the power of n is equal to E for all n not equal to 0.
For all positive integers k. I use k instead of n because my name starts with k and that makes it cooler.
Sounds
So if a has infinite order, we know that a to the k is not the identity element for any positive integer k. Oh, I don't know if I've ever explained what z plus means. Z plus is just positive integers. Shorthand of saying k and z such that k is greater than 0. So then, if a to the I is equal to a to the j, I claim we know a to the I minus j has to be equal to what? If we were to take, if a to the I and a to the j were equal, and we were to say multiply both sides of this on the right by a to the negative j, what would we be left with on the right-hand side of that equation? Right. The identity, indeed. So if a to the I and a to the j are equal, we know a to the I minus j is the identity, right? But if a to the I minus j is the identity, and a to the k is never the identity for any positive value k, what do we know about I minus j?
It's 0.
It's going to be 0. Yeah, so let's say, but since a to the I minus j is equal to the identity, and the order of a has to be infinite, thus I minus j is equal to 0, hence I equals j.
Why don't we have to consider like negative cases or anything less than 0?
Oh no, what if we said, oh no, why didn't we consider the fact that I minus j could be negative? We should. I'm going to consider it right now. There, I just considered it again. Without loss of generality, let's just assume that the I one, that whichever I is, we're going to assume is greater than or equal to j. Right? One of them has to be greater than or equal to the other one. So whichever one is bigger, we're just going to call I, and the other one we'll call j.
And so that also takes care of like I and j potentially being negative since.
Yeah, I and j could be negative.
Okay.
If I is -2 and j is -3, let's say, this same proof would still work. Because I minus j will still be positive, even if I and j individually are negative. So that's a good point, and something to consider. What if I and j are negative? So we've proven that if a to the I equals a to the j, then I equals j. We also have to consider the reverse direction. We have to show that if I equals j, then a to the I equals a to the j. That's really hard. Also, if I equals j, then a to the I equals a to the j. Oh wait, there's nothing to prove there. That one's easy. But it is another direction in our if and only if statement. When we show an if and only if, we need to show if first, then second, and if second, then first. So even though this backwards direction is really silly, yes, if I equals j, of course a to the I has to be equal to a to the j, it's still a direction that we need to consider and at least state out for it. So we've shown if I equals j, a to the I has to be equal to a to the j, and if a to the I equals a to the j, then I equals j. Thus, we've proven our if and only if statement, at least our first one. Thus, a to the I equals a to the j, if and only if I equals j. If a has infinite order. Any questions about this proof? Okay, I said this is a long one, and I meant it, because part 2 is a lot harder than part 1. We're going to get our hands dirty with some number theory here. So here's part 2. And this is going to be the case where the order of A is finite. So if A has finite order, I claim that A squared, etc., A to the n minus 1, and E all have to be elements in the group generated by A. Why is that? Well, we know that these all have to be in there because by closure, if A is in there, then we have to be able to take A star A, A star A star A, etc. over and over. Alternatively, by definition of a group generated by A, it has to contain all possible powers of A. So, in other words, we know that the group generated by A has to contain at least n elements. So we know pretty quickly that the group generated by A has to have at least n elements in it. It has to have these elements E, A squared, up to A to the n minus 1. The tough part is going to be showing that these are the only elements in the group generated by A. That if A has finite order n, the group generated by A can't have any other elements in it. So how can we show that the group generated by A can't contain any elements other than those? What would be a way that we could actually go through, or a general strategy for how we could prove these are n elements in this group generated by A, and that there can't be any elements other than those n? Right?
Like saying that there's more and then proving that those more are not in there?
Ooh. So like a proof by contradiction, suppose that there are more and then show something bad happens?
Yeah, sure.
Yeah, sure, maybe. That's certainly a way we could do it. What I'm going to generally do is I'm going to suppose that there is some other element in there and then prove that it has to be equal to one of these pre-existing ones. Which would be essentially the same idea learn as what you suggested. Say if there's another one that's not one of these, things go terribly wrong. There's a logical contradiction at some point. So I'm going to take an arbitrary element in here and show it has to be equal to one of these things. What do we know about all elements in the group generated by A? You know, they have to be some power of it, right? So we're going to let A to the K be contained within this group. Yes, net K may be negative, and that is a case we would have to consider. In fact, if we didn't consider negative K, this would be a lot easier to prove. What to do? We will show that A to the K is contained in this set. Because if we can do that, then if an arbitrary element of the group generated by A has to be contained within this set, that would be enough to then tell us that this set is equal to, that the group generated by A is equal to this set. If every element in this group has to be something in this set. So to do that, we're going to use our friendly neighborhood division algorithm theorem. The one that from last time that involved Q's and R's. Everybody remember that? We're going to use that. I'm going to say that by the division algorithm theorem, or the div algorithm, if you prefer, there must exist integers Q and R such that K is equal to Qn plus R, with R going to be less than or greater than or equal to 0 and strictly less than n. So here I'm using the fact that K is an integer n is an integer, and the division algorithm theorem tells us for any pair of integers, including k and n, we can come up with a q and an r that have to satisfy this result right here. Something that's true for any integers, therefore it has to be true for our k and our n. We have to be able to find a q and an r, and those have to satisfy that k is equal to qn plus r, where r is greater than or equal to 0 and strictly less than n. We also know q and r have to be unique, by the way, but that's not going to be important in our proof. Because check this out. I'm going to use that to say that a to the k, this thing that we'd like to show is in the set e through a to the n minus 1. A to the k, I claim, has to be equal to a to the power of qn plus r. But wait, we can split this up into a to the qn, a to the r. But wait, we could split this up even more to a to the n to the q, a to the r. Here is the clincher. What do we know about this thing? A to the n to the q. I claim we can say exactly which group element this thing is equal to. Rowan?
It should be the identity that the Q, which is the identity.
Bingo. And here is where we're finally going to use this fact. That the order of A is equal to n, which means A to the n, by definition, has to be the identity. So this is going to be the identity element to the Q power times A to the R power. Well, it doesn't matter what Q is. Yes, Nick, Q can even be negative. The identity element to any power is just going to be the identity element. This is the same as EA to the R, and that's going to be equal to A to the R. So it turns out this A to the K power is really just going to be, has to be equal to A to the R, where R is the remainder given to us in the division algorithm theorem. Here's the fun part. What do we know about R?
It's between 0 and n.
It's greater than or equal to 0 and less than n, meaning a to the r has to be a to the 0, a to the 1, a squared, dot, 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 or a to the n minus 1. In other words, a to the r has to be in this set. In other words, a to the k has to be within this set. Let's write all that down. Go ahead and erase part 1. Thus, a to the k is equal to a to the r for some r that's going to be between 0 and n. Hence, a to the k has to be contained in the set a squared up to a to the n minus 1. Because r has to match the exponent of one of these powers of a in this set. Any questions or comments about any of this stuff? Kind of relying on the division algorithm to show a to the k has to be one of these small, relatively small powers of a. Thus, we can say that since a squared up to a to the n minus 1 are all elements of a, and all, or in the group generated by a, and all elements in the group generated by a lie in the set a squared up to a to the n minus 1. Thus, this group is equal to, thus the group generated by A has to be equal to this set. By the way, if the group generated by A has to be equal to the set a squared up to a to the n minus 1, what does that tell us about the group generated by A? What has to be the order of the group generated by A?
Has to be n.
It has to be equal to the number of elements in the set with n elements in it. Has to be n. And there's our proof. The order, well, I'm not done proving the theorem, but that's kind of proving the result we said midway through class where I said the order of an element has to be equal to the order of the group it generates. We just showed that if A has order n, then A will generate a group of order n. And technically our work in part 1 will show that if A has infinite order, then we're going to get a group of infinite order as well that A will generate. Which justifies our use of the word order to mean two different things when really we're secretly referring to one thing. The order of an element can be used to define the order of a group, if the group is cyclic at least. Questions or comments? But wait, there's more. We haven't finished proving this theorem yet. We've proven this part, and we've proven this part. Still need to prove this part. That if a to the I equals a to the j, or that's true if and only if n divides I minus j. Meh. I don't feel like starting that group now. Y'all can go a couple minutes early today. I will, slight spoiler alert, we will finish this proof and then prove more things in class on Wednesday. And the proof of this fact, a to the I equals a to the j, if and only if n divides I minus j, is going to be very similar to our proof of the first half of number 2, in that we're going to use the division algorithm to help us arrive at this result. Okay, have a good day, everybody. I will see you all on Wednesday. Continue our discussion and get back into cyclic, proven things on cyclic groups.